strategy going to be for finding domain? Maybe we should start there.
I set the inner part of f, so the negative 1/2 x plus 2 equal to negative 3.
Good. And in fact, I think what you can do is just take all of this right here and plop it right where the x is, and then solve both ends together at the same time. Because you want when you plug this into here, you're going to want to know what's that outer boundary. So I believe we can go negative 1/2 x plus 2. Plug that right in where we have the original domain. So what we want is whatever we choose for x in here and whatever we do to it has to fit within these values of x ultimately. So then if you kind of unravel this, if we multiply through by negative 2, then that's going to be a 6. We're going to switch the direction of the inequality. We'll switch the direction of the inequality, and that'll be a negative 10. Right, okay? And then to get x completely by itself, we'll subtract 2 from everything. So there's where our 4 is coming from. But I think when you subtract 2 here, that should be a negative 12. And that's not going to equal to. Now that's written big to small, which is okay because the inequalities are facing the right way. But typically we'll write it from small to big. So when we do that, we'll switch those inequalities with them. And that's how we can come up with the domain.
What I got was 6. For x is less than or equal to 6 and greater than negative 10. So I forgot to subtract.
Subtracted 2 at the end, yeah.
Oh.
Okay. Aaron, we okay with that?
Yeah. Sure.
It gives you a strategy anyway, a way of trying to do this. Now the range kind of works the other way around. You're going to take what you've got and then do these things to it. So at least that's the way I think of it in my head. So we're going to take whatever y values we have. That's what's coming out of this f. That's going to get multiplied by 2 and then have 7 subtracted from it. So the multiplying it by 2 is going to make that be, this is in between now, so maybe I'll put it up here. So it's going to be 8 less than y less than or equal to 20. Then we're going to subtract 7 from everything. And so that'll be a 1 less than y less than or equal to 13. And that's going to be our range. Does that kind of make sense? Did you get a chance to look at this one? Okay, so kind of similarly, we can take whatever's the inside part here that has to do with the domain and set it equal to the x value there, and then solve it or kind of unravel it to see what value of x is going to give us a negative 6. And so if we take that negative 3 times x plus 1 equals negative 6, and then see what x is going to get us to there. We can divide by the negative 2 and then subtract the 1. So it's going to be an x value of 1. Okay? And you can kind of recheck yourself. If you plug in 1 into this, 1 plus 1 is 2. 2 times negative 3 is negative 6. F of negative 6, that's the only value of f we know, is going to give us a 10. Now that 10 that's going to come from all of this right here after we evaluate f of negative 6, we're going to take half of that 10, which gets us to 5, subtract 8 is going to be negative 3. So that's our point that's going to be on that curve. Okay? Okay? Right? Okay, these are tough. No way around that. Questions from the homework?
Part D from question 15 on homework 41.
Do you know what that is?
No.
Do you know what page it? What's that?
Do you know what that is? Maybe. I
Maybe?
think, is it the graphing one?
I'm not sure.
Do you know what page we're on?
I think it's 255, 256.
255.
I do not.
I'm looking for 15D. Okay, yeah, so it says the graph of g of x contains the point 6, negative 9. So g of, does that sound right?
Yeah.
6, negative 9. And then there's a part A, B, C, D. D wants a bunch. So let's see. We want to find a point on 1/2 g of 1/2 g of negative 5x minus 15. Does that sound right? Minus 8. Okay, so kind of like what we were working on here just a minute ago. Any ideas of how we might start?
We factor the -5 out.
You can do it either way, because I mean, you could factor it out. You could also just say, because what we're going to do, I think, or a nice way to do it, I would think, is to take whatever we have here, set it equal to 6, and then solve, which we can do by factoring or by not factoring. So if we just take the negative 5x minus 15 equal to 6, then we're going to solve that for x. So we're going to add the 15 and then divide by negative 5, and then that's going to be, yuck, negative 21/5. And then, okay, so it is messy, but now then whatever we get here, once we plug it in there, is going to lead to us evaluating g of 6, which is going to then make this part of it here be a negative 9. And so then we're going to get that, 1/2 times all of this is going to be our negative 9, and then minus 8. And that looks like it's going to be kind of messy too. So that's a negative 9/2 minus 16/2. I guess is going to be a negative 25/2. And that's something you're going to look at and guess. Okay, strategy. Anything else?
13C.
Same page? 13C. So 13C, let me. So 13C is saying, so f of x is the absolute value of x, and then we want to transform this. So we're going to start with y equals absolute value of x as our parent function. And then we want f of 2x plus 1 minus 3. So this is a tough one because it's not been factored. And so this is one where it's a little bit dangerous. It looks like it's going to be moved 1 to the left, but that is not correct. Because before we can tell the difference between the horizontal shrink and the translation, we have to factor it inside there. So the original, let me put that up there. We know the original absolute value of x is going to look like this. And in particular, like we talked about last time, if you saw the video anyway, it's going to contain the point 0, 0, and it's also going to contain the point 1, 1. And in this case, because of the symmetry, that means it's also going to contain the point negative 1, 1. So we can see what's going to happen to this point 0, 0, and that's going to be just the translation part. And then we can see what's going to happen to this 0.11, taking into account the vertical and horizontal stretch and shrink, whatever may happen. So this, we can, if we factor that 2 out, can you see what that's going to become? What will that be?
X plus 0.7.
Yeah, x plus a half or x plus 0.5. So that means that we're going to translate our 0.00 is going to go left a half and down 3. So I think I'll just give it a new graph here. So we're going to go left. So there's -1 and down 3. So I'm going to put that point right here at -1/2, -3. So that's going to be our vertex there. Now, without any stretches or shrinks, we would just go up 1 over 1 from that point and get a second point, and we could go up 1 and left 1 and get another point. But here, because of this is a horizontal, stretch or shrink? Shrink. We're going to go up 1 and over a half. So we're going to go up 1 and over a half. Since we're at -1/2, that's going to put us right here on the y-axis. And that point is going to be 0, -2. And then because of the symmetry of our absolute value, we can also go up 1 and over a half the other direction to the left. And that's going to put us right at -1, -2. And then these are going to be straight lines coming out there. And that's what I'd be looking for on that question. Okay, anything else? Okay, so we are at a place now where we're kind of changing gears here. So I may have mentioned at the beginning of the year, there's kind of 3 very distinct kind of stretches in this class. And the first part has been kind of like an Algebra 3 or an extension of Algebra 2 kind of stuff. Now we're about to switch over and start doing the trigonometry part, which is a big 2-3 month section we'll do. And then we'll change gears again in the late winter, early spring there, where it's going to become more pre-calculus type stuff there. So we're going to start on our trig adventure here. And so this is going to start with, I'm going to kind of review some of the stuff you've done from your geometry days. We're going to simplify radicals. We're going to talk about special triangles like 45, 45, 90s, 30, 60, 90s. And we'll revisit the SOHCAHTOA, the right triangle trig, how you get sine, cosine, tangent from a right triangle. So this is now a review of simplifying radicals. So I'm going to grab a bigger piece of chalk here. So if we want to simplify, say, the square root of 50, then we're looking for what are the perfect squares that go into 50, because we can pull those out. And I know some of you learn to do factor trees, and you're fine to do that if you like. I'm not going to do that here. I find that a little bit tedious personally. But if you just look for what are the perfect squares, and by perfect square I mean 2 times 2, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. And we can see that 50 is what perfect square times what?
5 squared times 2.
Yeah, so since 5 squared is 25, we can think of that as 25 times 2. And then the square root of 25 is just 5. And so we will simplify it to be 5 squared root of 2. We've seen that before, so we're okay with that. So to add and subtract radicals, if we take 3 square root of 8 plus 5 square root of 18, if the insides of the radical are known as radicands, so whatever is inside here, that is called a radicand. That's just kind of a trivia question there, but just so we have a name that we can give it. So if the radicands are the same, we can add those, but if they aren't, we cannot. But here we can simplify first and then see where that leads us. So what multiplies to be 8 that's going to be helpful? 2 times,
Two square root.
yeah, so 4 times 2 is 8, right? So square root of 4 becomes 2 outside the radical, multiplies that other 3 that's outside the radical, and so that's going to become 6 square root of 2. And how about with the 18?
9.
Yeah, it's 9 times 2, and the square root of 9 is 3, multiplies that 5 and becomes 15. And now because our radicands are equal, it's like adding 6x to 15x, we can add their coefficients. And so that'll be a 21 square root of 2.
Did I multiply 15 by 3? No, I was 5. I thought it was 15 to start with.
Okay, now, yeah, it was supposed to be a 5. Okay, we're all doing the same problem, we get the same answer? Okay. Let's do some more. Let's say we have, now you can only add and subtract like terms, but we can multiply and divide anything. So when we have 2 square root of 5 times 3 square root of 15, it's really all these multiplications. The 2 is multiplying the square root of 5, which is multiplying the 3, which is multiplying the square root of 15. So we're free to shuffle the order any way we like, and the things that are outside the radical we can simplify to become 6, and the things that are inside the radical will also multiply and become 75. See how we got to here? Now we can simplify square root of 75, because what multiplies to be 75 that's helpful? Yes, 25 and 3, so that's going to be square root of 25 is 5 times the 6 is going to make that 30 square root of 3. Are we okay to that? And if we have something that, like say 4 square root of 3 squared.
9 times 16.
Yeah, exactly. So it's like what we did here, 4 square root of 3 times 4 square root of 3. Or you can think of it as the 4 squared and square root of 3 squared. Either way is correct. So the 4 is going to get squared and become 16, and the square root of 3 is going to get squared and become
9.
yeah, square root of 9, which is 3, or you can think of it as removing the radical. Either way is okay. So we're going to get 16 times 3, which is 48.
Stop
That
and
okay?
think about that.
Oh, yeah. Now, if we have something like, say, 5 over square root of 3, this is not considered simplified. It's kind of, historically, it kind of goes back to more easy access to calculator days. So square root of 3, square root of something that doesn't come out even is an irrational number. That's a non-terminating, non-repeating decimal like pi. So if you can imagine, if you didn't have a calculator and you were going to try to divide something, divide 5, you're putting that inside the division symbol by something that never terminates and never repeats, it's really hard to do. On the other hand, if you make the irrational number be in the numerator, having whatever it may be that doesn't terminate, but dividing by something that is rational, that is at least is doable. Because you could start with the division and you could go to as many decimal places as you like and then round. Whereas you can't really do that if the non-terminating decimal is on the outside. Of course, now everybody's got a calculator, and so it's not that big a deal, but the idea still survives kind of historically that we want to give this as an answer that does not have the radical in the denominator. To do that is called rationalizing the denominator. And so what do we do?
You multiply by
What do we do again?
multiply by the square root.
Yeah. So we're going to multiply top and bottom by the square root of 3. So we're multiplying by 1 in a strange form. Because what that does in the denominator is get rid of the radical. So square root of 3 times square root of 3 is 3. And on top, there's not really anything we can do, so that's just 5 square root of 3. And you could make an argument that that's not really much of an improvement over where we started, but historically, this was a better thing. And so it kind of survives as just kind of something that never goes away and torments students.
Kids these days with their calculators.
I know. Back in the
Back
day.
in his day,
Yeah.
back in his day, they used slide rules.
Oh, that was even before my day. So let's see if we can simplify this. So see what you can do. And then we'll see if we agree on what that final answer should look like. Should end up with something that combines if you're doing this right. So we're going to get a single term answer. Hopefully. So Colby, what do we do with the 6 over square root of 2?
Multiply it by square root of 2 over square root of 2.
And so that's going to become what?
6 root of 2 over 2.
Which is going to simplify further to be
3.
Caden, what about square root of 98? What in the world multiplies to be 98?
49 and 2.
Nice. And square root of 49.
7.
And so now they have become like terms, and so we add them and get
10 squared root of 2.
10 square root of 2. That okay? Okay, so changing gears, we'll talk about Pythagorean theorem and special triangle.
Okay.
Pythagorean theorem and special triangles. And Pythagorean theorem is old. This goes back, I think, I can't remember, that was 1000 BC, or Pythagoras was a Greek mathematician, but there's evidence that the Chinese knew about that even earlier than that. It's been around a long, long time. So we know that in a right triangle, so typically we call this A, B, and C, leaving the right angle to be the C, and we name the sides opposite. So the angles get named with capital letters and the sides get named with small case letters. So side little a is opposite angle A, side little b is opposite side angle capital B, and side C is opposite the right angle, and so which is capital C. And so the two angles that make up the right angle are known as legs, and the side that is opposite the right angle is known as the hypotenuse. And so if a triangle is a right triangle, then we know that C squared is equal to A squared plus B squared. Now, so in the language it says if triangle ABC is a right triangle. So theorems are written as if-then statements. If triangle ABC is a right triangle, then we know that C squared is equal to A squared plus B squared, or we can say the square of the hypotenuse is equal to the sum of the square of the legs. Now, an if-then statement can be true. What it means to be true is anytime the if part, the condition, is satisfied, then the conclusion also follows. The converse is not always true. If you switch the order, sometimes it's true, but sometimes not. It depends on what the theorem is. So my favorite example is I say, if you give Mr. Street $1 million, you will get an A in this math class. That's a true statement. Every student that has given me $1 million has gotten an A. Sadly, the converse is not true. If you get an A, then you gave Mr. Street $1 million. Unfortunately, there have been a couple of A's over the years, and still I haven't gotten my first $1 million. So you see how the converse words, switching the X's, the if and then around. The Pythagorean theorem is a case where the converse is true. So the converse, That's what it means when you switch the if and then parts. The converse of the Pythagorean theorem, which I'm going to abbreviate there, that's the Pythagorean theorem, says if c squared is equal to a squared plus b squared, then triangle ABC is a right triangle. So it's a way of proving that a triangle is in fact a right triangle if their sides fit that form, c squared equals a squared plus b squared. So the question is this triangle a right triangle? And I'll give you the side lengths. I'll make it looks hypothetically like it could be a right triangle. I don't know. You're going to have to decide that. We'll call this 3 square root of 2, and this 2 square root of 3, and this square root of 30. So what does that mean we have to do if we're trying to answer the question, is this a right triangle? So we're going to take whichever one looks like the biggest one, and I'm going to put a question mark over the equal sign. So is that longest side squared equal to the sum of the squares of the other two sides?
Yes.
And you believe that? So square root of 30 squared is 30. 3 squared of 2 squared is 3 squared times square root of 2 squared. That's 9 times 2. Good. And 2 squared of 3 squared is the 2 squared times the square root of 3 squared. The 2 squared is, and the square root of 3 squared is. So sure enough, that is true. And so our conclusion is yes, it is in fact a right triangle. Okay, so let's from here talk about some of our special triangles, and one of those is what we refer to as a 45, 45, 90 triangle. So a special case of a right triangle. And in a 45, 45, 90, we know that we have a right angle, so there's a 90-degree angle.
And the legs are,
And the other two angles are the same, so they're both 45 degrees. From your geometry days, you remember that if two angles of a triangle are congruent,
the legs are congruent.
then right, the sides opposite are congruent as well. So a 45, 45, 90 is also known as, what do you call a triangle where two sides are congruent? Nice, you guys are good. So this is also known as an isosceles right triangle. So there's a special relationship between the sides here that's unique to 45, 45, 90s. And so we're going to use the Pythagorean theorem for a minute here and then see what that relationship is in the 45, 45, 90. So if these are both x and we want to see what is the hypotenuse in terms of x, you with me here?
Sure.
Then we can do Pythagorean theorem and say x squared plus x squared equals c squared. That makes sense? And x squared plus x squared is 2x squared. Is that okay? And then solving for c, we'll take the square root of both sides. And then we'll kind of squint at that for a minute and say, we can say that the square root of 2x squared is x squared of 2. And technically, I want to plant the seed a little bit here. Technically, the square root of x squared is not x.
No, it's plus or minus.
Not plus or minus x. It's actually the absolute value of x. Because what this symbol means is called the principal square root. So it's the non-negative square root. So any positive number has two square roots, right? The square root of 25, there are two of them, 5 and negative 5. This symbol always means choose the one that's not negative. So that is only equal to 5. Where the confusion with the plus or minus comes in is we kind of do this loosely when we're learning. Yeah, so if you're solving an equation and you use that as an operation, like you say, oh, let's take the square root of both sides. What you're really getting is you want all possible solutions, which means you want all of the square roots of 25. So notice what we really should say, but we don't do this very often, is we want the positive and negative principal square root of 25. This symbol is only the positive 5, but because we want all possible solutions to this equation, we get positive and negative 5. But this symbol itself does not equal positive and negative 5. It's only positive 5. Now here we don't really have that issue. This will be an issue later, not in this question, because we're talking about side lengths. And it wouldn't make sense yet for us to think about a side length of a triangle being negative. And so we can not worry about it and just call it x squared of 2, because from the context of the problem, this x is not going to be negative. Okay, so long story short, we're going to call this x squared of 2. You need to remember this relationship or be able to recreate it because it comes from the Pythagorean theorem. So I can ask you questions like, here is a isosceles right triangle, and if this side is 7, then can you figure out what is side length m?
7 square roots of 2.
Right. And so we know that this is the x, this is x times the square root of 2, so the m is going to be 7 square root of 2. That was a warm-up, okay? I'll try to disguise the isosceles right triangle here. So I'll try to turn that triangle around. It's probably confused you, but it's actually a 45, 45, 90. And this time we'll say this is 10, and we want to find that side length n. Now you have to do a little bit of work, right? The 10, because it's the hypotenuse, is equal to x squared of 2. So we'll say 10 is x squared of 2, and now you've got to solve for the x. So to solve for the x, we're going to have to divide by square root of 2. Now we have to rationalize. So we're going to multiply top and bottom by square root of 2. That takes us to 10 square root of 2 over 2, and then we can simplify the 10 over 2 part. So the long and winding road takes us to, n is going to be 5 square root of 2. Good to go?
And you put 5 square roots of 2? Or would the 10 is equal to 5 square roots of 2 though? So would n would be 5?
No, no, no,
X
no,
equals
no.
5 square root of 2.
Yeah, x is 5 square root of 2. So this is going to be 5 square root of 2 times square root of 2.
Oh,
which is 10.
That's
Which
the
is 10.
easy way to do it. I guess
Yeah.
I went the long way.
Does that make sense?
Yeah.
So we're still consistent. It's fitting our relationship between the side lengths is still true. Okay, well, let's try to make things more complicated and look at a 30, 60, 90.
I miss geometry.
The good old days.
Back when math was like so easy.
Yeah, back when you didn't have to do homework and it didn't cost you. Huh? Oh, I'm sorry, did I say that out loud?
Hey, whoa, I did not come here to get shaded by Mr. Street.
So
Whoa,
this-
you're here anyways. I'll leave, I'll do it.
This is an equilateral triangle, which is also from your geometry days, more than isosceles even,
A 60, 66.
which is called equiangular. So not only are the 3 sides congruent, so are the 3 angles, which means since the angles add up to be 180, that they're all going to be 60. So at least to start with. Now I'm going to call these side lengths here because I have ulterior motives. I'm going to call them each 2x. Right? So they're congruent. So that's an equilateral triangle, and we'll just name the side lengths as 2x. So we can then, from here, we'll drop a perpendicular down from one vertex, from one angle down to the opposite side. Now, once that becomes a 90-degree angle, then we can see that we have 2 congruent triangles, And since those are congruent, that means these two angles up here for the right triangles must split the 60 degrees evenly. And so we have created a 30, 60, 90. In fact, we've created two congruent 30, 60, 90 triangles. Does that make sense? So I'm going to pull one of those out. I'm going to pick the one on the right. Doesn't really matter. So here is our 30, 60, 90. We okay so far? Now, because I chose this side to be 2x, that remains 2x. Because when we dropped this perpendicular down, we created two congruent triangles. This side down here, that 2x, has now been split into two congruent segments, which makes this side length now x. Does that make sense? We still have a right triangle, so the Pythagorean theorem still holds. So we know these two sides, and we can solve for that side. I'm going to call it a for a moment, but I'm going to come back and get it in terms of x. So from Pythagorean theorem, we're going to get a squared plus the x squared, right? Those are the sum of the squares of the legs, must be the hypotenuse squared. Remember, we're squaring the quantity 2x. You with me? So on the left side, that's just a squared plus x squared, but when we square out the 2x squared, it's going to become 4x squared. We'll subtract 1x squared from that 4x squared, which is going to make a squared equal to 3x squared. Now, like we did before, when you okay with that, Paige?
Yeah, I think so.
Okay. Slow down a minute so you can digest. Okay, now, like we did with 45, 45, 90, we're going to solve for a, so we're going to take the square root of both sides. So we're taking the square root of 3x squared. We had the discussion about the square root of x squared, but I want you to have kind of a little buzzing noise in the back of your head that says that's not really x, but in this case, because we know x has to be positive, we're okay with not calling it absolute value x and just calling it x times the square root of 3. So that tells us now, and let's just make sure that this makes sense because people struggle with getting the right order here. We know that the angles inside here go from a smallest of 30 to a middle of 60 to a largest of 90, right? Small, middle, big. Okay, now the sides opposite go in the same order, right? Opposite the smallest angle is the shortest side. That's 1x, or the square root of 1 times x. The middle angle, the 60, is opposite them. It's called the longer leg. This is the short leg, the long leg, which is the middle-sized length here, because square root of 3 times x is bigger than square root of 1 times x, but less than the square root of 4 times x. Right? Square root of 1x, square root of 3x, square root of 4x. Short angle, short side. Middle angle, middle side. Biggest angle, biggest side. So it's keeping the order of the x squared of 3, and 2x. I think that's important, so you can get them labeled in the right way. Short leg, long leg, hypotenuse are the names that are given to those. Okay, so now we know that relationship, I can ask you more questions. Like, suppose we have a right triangle here, and we know that this angle is 60 degrees, and we know that this side is 8, and now I can ask you what is m and n both. And so I'll give you a moment to solve that. So the 8 is equal to, is it equal to x, 2x, or x squared of 3? 2x. 2x. So that means the x must be 4. And which is the x, the m or the n? M. So that's the short leg, so that's the 4. And that means the n must be 4 squared of 3. I'm getting short on time here. Got much more we will come back to and do here. Let's first refresh our memory on SOHCAHTOA, which is how a lot of people learn this. Personally, about 10 years ago when I was in high school learning geometry, my geometry teacher said sin cos tan, right? If you get in trouble, you get hurt. And Oscar had a heap of apples. But I've tried to be flexible and incorporate the SOHCAHTOA method as well. So the idea is that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. Has anybody not heard that before? Okay, so in a right triangle, so you have to have a right triangle. And so if I call this, say, angle A, angle B, angle C, side A, side B, side C, then we know that the sine of angle A is going to be the opposite over the hypotenuse. And so that's going to be A over C. Okay, well, I haven't done any examples here and I'm about out of time, but I'm going to trust that you remember this, but we'll spend 2 days on this. So we're going to talk more about this. I have a worksheet for you here that you just do the odds today. Don't be an overachiever and do the evens, because I think we should discuss them first on Monday before we do the evens. It does have the work solutions there, so you can
I'll
consult.
trade you can give that to Colton.
Oh,
Thank you.
you are welcome. Remember, we got a test tomorrow. You sleep in until 9:30 unless you have any physics, in which case you can come anytime you like as long as you have 9:30. Is it every physics? Oh, not just AP.
Yeah.
Oh, you have one.
We also think that we went to one of the AP conferences and had a test, but we have a test here.
Yeah, no, you dropped it. Oh, you dropped it.
3 hours in testing.
I bet you the physics don't think you know. Okay.
I want to steal it.
Do you need one?
No, I don't know.
Okay, you just have to, it's too lazy to get it out of your backpack?
Yeah. Thank you.
All right, you see ya.
Oh, I was gonna mention, calculator, my dad says that when he was in high school, the calculator had just come out.
Yeah, but not graphic.
No, it was just like
No.
super calculator,
Okay.
brand new.
And they were expensive too,
Yeah.
yeah, it's
Like if you had a calculator, it was cool.
No, it was.
And now it's like the latest thing.
I know, like, I mean, they give them away, you got watches, you got, it's like, yeah, it's so expensive. Yeah, well,
That was interesting.
yeah, it is. You're not running away from home, are you?
No, I'm just really cold this morning.
Lunch and all of your possessions. The